One way out of this dilemma of why is it so big is if it was targeting the inner solar system by design. And indeed, the trajectory is aligned with the plane of the planets around the sun to within 5 degrees. The chance for that at random is 1 in 500, okay? And it's moving in a retrograde trajectory opposite to the motion of the planets, which is ideal for it to release mini probes that will get into the planets. It gets close to Mars, it gets close to Jupiter, it goes on the opposite side of the sun relative to Earth when it's closest to the sun. And that's the time when a spacecraft could do a maneuver to take advantage of the sun's gravitational assist. All of these are interesting indications that may imply that some intelligence designed the trajectory. So I had one sentence at the end of the paper saying maybe the trajectory was designed.
When scientists calculate the probability of an object striking Earth, the process sounds deceptively straightforward. They measure its position, velocity, and acceleration, then feed those values into models that project the orbit forward. But what the public rarely sees is that these calculations rely on absurdly small angles, sometimes fractions of a degree so tiny they are barely measurable through atmospheric distortion. A microscopic shift in the object's path at millions of kilometers away can cascade into a completely different outcome when it eventually crosses Earth's orbital region. With familiar comets and asteroids, this uncertainty is manageable. They orbit the Sun in stable, predictable cycles. Their outgassing behavior is well understood. Their shapes, densities, and rotational patterns fall within known ranges. But interstellar visitors like 3I Atlas come with no such advantages. Their origins are unknown. Their structures are irregular. Their surfaces react to sunlight in ways we cannot anticipate. The precision needed to predict their paths becomes nearly impossible until they are uncomfortably close. This is precisely the issue Avi Loeb highlighted. The danger is not that an interstellar object is likely to hit Earth. Statistically, the risk is low. The danger is that if one were ever on a collision course, astronomers would not be certain until late in the trajectory when the object's path becomes sharply defined. And by that moment, the remaining time for action could be measured not in years, but in days or even hours. It is this compression of the decision-making window caused by mathematical uncertainties no one can remove that makes interstellar impact scenarios uniquely challenging and fundamentally different from anything humanity is prepared for. Interstellar objects do not behave like ordinary comets, and 3I Atlas is a perfect example of this. Observers noticed early on that the object's brightness and shape were not symmetrical. Instead, a single, consistent jet of material appeared to be escaping from one side. In a normal comet, this might signal uneven heating, but with 3I Atlas, the jet remained angled in the same direction over consecutive observation nights. This introduces a serious scientific complication known as non-gravitational acceleration. Imagine trying to predict the path of a drifting log in a river. You measure its speed, direction, and distance. But then the log begins to slowly release air from one side, pushing itself in unexpected ways. Even tiny forces acting consistently can shift the object significantly over long distances. That is precisely what 3I Atlas may be doing. Non-gravitational drift is not just a small annoyance. For an object travelling at interstellar speeds, even a delicate jet of escaping gas can push the orbit sideways by thousands of kilometers over the course of weeks. This means that standard trajectory projections become outdated quickly. Every time the jet strengthens, rotates, weakens, or divides into multiple streams, the orbital calculations must be restarted. This is one reason Avi Loeb warns that if such an object were headed directly for Earth, we would struggle to identify the danger early enough. The orbit would appear safe at one moment, only to shift dramatically later as the object's internal activity changes. In the case of 3I Atlas, scientists are tracking these irregularities carefully. But the deeper message remains the same. A moving target with its own unpredictable thrust cannot be forecast with long-term confidence, and by the time its real trajectory becomes known, the options to prevent disaster could already be gone. Contrary to public belief, astronomers do not scan the entire sky every second of every day. Most telescopes have limited fields of view, and most sky surveys focus on predictable regions, where long-period comets and near-Earth asteroids typically appear. Interstellar objects, however, arrive from unusual directions at very high speeds. They often approach from above or below the ecliptic plane, the thin disk in which planets orbit the Sun. This means they can remain undetected until they are already very close. The problem is worsened by their low reflectivity. Interstellar objects often appear extremely faint until sunlight heats them enough to produce outgassing. Only then do they brighten, and by that time they may already be deep inside the Sun-Earth system. This delay in visibility makes early detection unreliable. Even with advanced telescopes, atmospheric distortion, moonlight, and the angle of approach can mask them until the final stage of their journey. 3i Atlas itself became noticeably brighter only when it reached regions where solar radiation was strong enough to ignite activity at its surface. Before that, it appeared as a dim and uncertain target. If an object on a collision course behaved the same way, astronomers would have no way of knowing until it was practically upon us. And because these objects travel faster than anything bound to the Sun, the available reaction time collapses. Days become hours, hours become minutes. This is why Loeb emphasizes that detection systems designed for predictable, inner solar system threats cannot be relied upon for interstellar visitors. The most dangerous object is not the one we track for decades. It is the one we see only at the end, just before its trajectory reveals the truth we did not want to face. One of the defining features of interstellar objects is their extraordinary speed. They travel faster than anything native to the solar system because they are not gravitationally bound to the Sun. Instead, they are simply passing through. This gives them a hyperbolic trajectory, a path that bends slightly as they approach the Sun and then slingshots back outward. The consequences of this speed are profound. First, it means that observational windows are short. A telescope may only catch a few nights of clear visibility before the object moves out of range. Second, because the object is accelerating due to the Sun's gravity, its path changes more rapidly as it approaches perihelion. This compresses the time available to confirm whether the object will pass safely or intersect Earth's orbit. From a planetary defense standpoint, speed is the greatest limiting factor. Current technology cannot intercept a fast-moving inbound object with only weeks of warning. Spacecraft need months or years to travel significant distances. Even kinetic impactors like the one tested by NASA's DART mission cannot be deployed in time if an object is detected late. This is why Loeb stresses that no realistic defense exists for fast interstellar threats. The physics simply does not allow enough time to maneuver spacecraft, test strategies, or launch countermeasures. In practical terms, the only viable strategy for such objects is early detection. And as we saw in the previous chapter, early detection is often impossible. The combination creates a dangerous paradox. The fastest objects give us the least warning, yet they cause the greatest uncertainty. Speed does not just limit our ability to react, it erases it. In most cinematic depictions, humanity sees an asteroid coming years in advance, debates strategies, launches missions, and ultimately saves itself. The reality for interstellar impacts is far less dramatic and far more abrupt. If a fast-moving object were headed directly toward Earth, one of the first definitive indicators might not come from telescopes. It could come from upper atmosphere sensors designed to detect high-energy intrusions. As the object enters the upper atmosphere, friction heats its surface instantly, producing an expanding sphere of ionization. Satellites, military sensors, and atmospheric instruments would detect this glow almost immediately. It would be unmistakable, but by that moment, the timeline would be measured in minutes. The object would already be descending toward the surface at tens of kilometers per second. There would be no global alert system ready to react, no coordinated emergency protocol, no space-based shield to intercept it. Civilization is not structured to respond to instantaneous cosmic threats, not because we lack intelligence, but because such events require infrastructure that does not exist. This scenario is what makes Loeb's warning scientifically grounded rather than speculative. The danger is not the probability of impact. Again, it remains low. The danger is the lack of response time if the improbable ever becomes real. For scientists, this is not a hypothetical exercise. Earth's atmosphere has recorded several large airburst events over the past century where detection only occurred at the moment of entry. All of those objects were small and relatively slow. A hypervelocity interstellar object would be exponentially more energetic. and by the time we recognized it, the event would already be unfolding. A core mystery surrounding 3I Atlas is whether its nucleus is intact. Many traditional comets fragment as they heat, breaking into smaller pieces that follow similar or diverging paths. But interstellar objects are different. Their internal structures may be layered, porous, metallic, fractured, or chemically unusual due to their origin in extreme galactic environments. Observations of 3I Atlas show subtle elongations, variable brightness patches, and shifting asymmetries. These suggest that its core may not be a simple solid object. Instead, it could contain internal voids or fissures that respond unevenly to solar heating. If such regions weaken, a fragmentation event could occur suddenly and without warning. Fragmentation dramatically complicates predictions. When a nucleus splits, the resulting pieces begin to influence each other gravitationally. Some decelerate, others accelerate, some rotate into new orientations that cause unexpected gas jets. The original trajectory becomes meaningless. Instead, astronomers must calculate the paths of multiple fragments, each with its own unpredictable physics. For Earth, this matters because even if the primary object misses us, a fragment could still pose a risk. Fragments are also harder to detect because they are smaller and dimmer, making late-stage identification even more challenging. While there is no sign that 3I Atlas is currently fragmenting, the patterns in its light curve raise legitimate questions. Its stability seems fragile yet strangely organized. Some scientists suspect that the object may have endured a violent past, such as collisions in a dense star-forming region. Whether or not fragmentation occurs, the mere possibility highlights why interstellar objects require a different risk model. It is not the object we see that poses the threat. It is the one hiding inside it. As 3I Atlas continues its journey through the inner solar system, its presence reminds us of something larger than the object itself. Every new observation, every small shift in brightness, every subtle change in its halo invites us to look beyond familiar models and consider the universe as it truly is, vast, unpredictable, and filled with travelers shaped by environments we may never fully understand. Avi Loeb's warning was never meant to spark fear. It was an invitation to awareness. Interstellar visitors are rare, but they are real, and each one becomes a lesson in humility. They show us how much we still do not know, how fragile our assumptions can be, and how important it is to expand the tools and strategies we rely on to understand the cosmos. 3I Atlas is not a threat to Earth, but it is a symbol of the limitations in our current detection systems, our defensive capabilities, and our ability to respond to fast-moving events beyond our control. Its behavior pushes the boundaries of what we can explain, encouraging scientists to study deeper, observe closer, and question more boldly. For now, we continue watching, not with fear, but with curiosity. Every night brings new data. Every shift in the object's appearance opens another chapter in a story still being written. And as long as it remains visible, it reminds us that the frontier of discovery is not behind us. It is unfolding in real time. If you want to follow these developments as they happen, remember to like and subscribe. We cover interstellar objects, space weather, solar activity, and the hidden patterns that shape Earth's environment from beyond the horizon. The next update may arrive sooner than expected. Until then, stay observant, stay curious, and keep looking up.